Hi, I'm going to talk about abstraction and complexity management today, and that's kind of a vague description, but I hope that you'll see what I mean as we go on. So if I might want to add, if I get more dishevelled or whatever as we go throughout, this is because I'm recording this in a conservatory and I've had to close all the doors and windows to avoid lingering sounds of birds. So it may be a bit hot in here. But anyway, I'll power on through that. What do I mean by abstraction in this context? Well, there's kind of a lot of debate about an exact definition for abstraction. So instead, I'll stick to more general definitions, and you can, if you want to work out exactly what is meant by a particular term of abstraction, you can go look that up yourself. Throughout this, I'll be using two definitions for abstraction. So the first one is mathematical abstraction. This isn't really the kind of abstraction that's the focus of this talk, but mathematical abstraction is the basis of the majority of abstraction we see in sciences. So, vaguely defined, I would say that mathematical abstraction is the process of removing dependence of mathematical concepts on the real world. So in other words, this is abstraction through elimination of needless information. So we get rid of the stuff that we don't need, and we're left with a form of abstract representation that is more general than what we started with and more widely applicable. The key thing here being that we do this by eliminating information that's not necessary. I'll have an example of that in a minute. The second form of abstraction, which I would do computational abstraction throughout this, but really it's almost a different concept with a lot of similarities, is broadly defined as the process of hiding details of implementation. So instead of eliminating information, we are hiding the information or hiding the detail behind a layer of abstraction. So again, I'll refer to this kind of as abstraction through information hiding. The commonality between the two is they both make something more widely applicable and more abstract, but one is a reversible process and the other is a more general and still applicable but not reversible process. So I'll start with an example of mathematical abstraction and what I mean by that. So if we have a look at an example here, let's look at asymptotic complexity. So this is something still in computing, but is an abstraction of the mathematical variety. So asymptotic complexity is the idea of when we are analysing the complexity of some algorithm, we take the algorithm and we remove the unnecessary layers to get an abstract asymptotic representation of that. So in other words, we perform several layers of abstraction on what's actually happening. First of all, we generalize all operations to be equivalent. Then we just change the number of operations that happen into some kind of reliable formula based upon n, which approximates the number of operations that need to be performed. And finally, we take the asymptotic form of that. In other words, we say, as it tends to infinity, what is the most important term? So here, at every step, we've removed some information, but we're still left with something that's useful, and in fact is possibly more useful than the original representation, as it allows us, in a general way, to compare different algorithms and their complexities. So we've eliminated the information which is not required, and that allows us to abstractly analyse it. So that's what I meant by information elimination. We've removed some of the information in the original, and we're left with something that is more representative of the general case. So now that we have an idea of what I mean by mathematical abstraction, let's have a look at how we use abstraction to consider computational abstraction. So fundamentally, computers are complex systems. And due to this, the only practical way to control them is through layers of abstraction. Without this, really what we'd be doing is a load of very, very complicated electronic engineering. So we would be considering exactly which electronic signals lead to which outputs, which, while doable, is immensely difficult and is something that we moved past quite a long time ago. And we did that through layers of abstraction. We abstracted the electronic engineering with even the most basic of codes, assembly languages, etc. Even the microcode on a modern CISC CPU, or a lot of CPUs nowadays, is an abstraction of the operations actually being performed by the CPU. So here we've taken all the operations, all the layers of complexity, and we've built a number of abstractions on top of that. Say assembly language, which is an abstraction of the instructions run by a machine. We may have more instructions in assembly language than are actually possible on a machine. However, we can reconstruct the raw instructions from the abstraction, and there, again, we're seeing that information is hidden but not removed. We can still reconstruct a lower layer representation. In fact, that is integral to that kind of abstraction. So here's an example of that kind of abstraction. Operating systems. The way that all applications interact with operating systems, and operating systems themselves are abstractions. An operating system has the difficult job of taking the low-level hardware, or the level that hardware allows interaction with it, and abstracting that further away into a form that is more accessible and more useful to higher layers. It does this through many different tasks like scheduling, resource allocation, and all of this is hidden behind what's called an API, or many APIs. These are application program interfaces, and these are fundamentally a form of abstraction. We'll talk about those in a minute. But we're left with this generic interface which abstracts away the computer underneath, which allows us to use the same software across many different computers without needing to modify it, because fundamentally it is a more abstract form of software than on the lower layers. Now, this can be seen in many places in operating systems, the use of things like virtual memory instead of physical memory, of virtual resources, and frequently these are the terms that are used, but really what we're seeing here is an abstracted representation of the machine versus a more accurate representation of the machine. Not to say that the physical representation the OS sees isn't an abstraction itself. And all of this is done to provide a common layer. And this is really the importance of abstraction in computing, that it can provide an abstract common layer like this, or at least one of its benefits. So in general, as we saw there, an API is one of the ways that abstraction shows itself in computing everywhere. An API being an application program interface, as I previously said, and they are one of the main ways in which abstraction shows itself. An API is basically just a fixed or somewhat fixed interface to a set of lower level procedures which allow other programming concepts, etc., to be built up, and so on. This is useful with, say, OSs, in that an OS can provide an API for getting memory or something like that. And then every application has a consistent way in which it can allocate itself some memory, and it has a consistent way in which it can then free that memory, i.e. say that that memory is no longer in use. And that fixed interface can be the same across many different machines without having to know how much memory a machine has, where that memory is, what address it may take up. And APIs can also allow a more general outlook on this kind of thing. So an outlook where we're talking about generic resources instead of specific resources. And of course, it allows us to use these generic resources across many different applications. If we have an API on a library, and if a library exists that has an API that allows us to, as I said before, do something like allocate memory, then we can use that across many applications. Now, an example of a massively important API, as I said, operating systems tend to have APIs, and the main one in Windows is the Win32 API. Technically it's the Win64 API now on 64-bit computers, but most people still refer to it as Win32 through force of habit more than anything. So it's one of the core, if not the core way of interacting with Windows operating systems since Windows 95, and as such is a very important part of Windows operating systems. And it has a lot of functions which are required for interacting with different parts of Windows, including the windows of Windows. So just taking one example of this, we have the getWindowText method. And there's actually multiple forms of this method, but in general the idea behind it is it gets the, well, typically the title text of a window, the thing that appears across the title bar. However, this is not always the case, and there is a lot of complexity behind the scenes that is abstracted away by this API, because in fact this can be used on windows that do not have a title bar, but they may still have a text element. And there's many more complexities to it, such as the fact that it claims that it only works on windows that the process that's running it owns, as though this is not actually the case. But for historical and complex reasons, it's better to not use it across processes. And it's things like this, that complexity, which can be abstracted away by the use of an API. So when I go read about this function, I don't need to know that it can actually be used for other things, and that's not helpful to me. If it is, and if I do use it like that, I'm using it against the way that it's intended to be used, which may in turn lead to issues, as I'll get onto. So the way that most APIs and libraries and the like perform abstraction is to effectively do one of two things. Either they are simply providing a different interface, rearranging the interface that exists, or more commonly, they change the functionality provided. So they use some kind of lower level interface and they provide a higher level or equal level but different interface, which makes it easier to do a particular thing. And they do this mainly by assumptions. They bake in assumptions to the API which control how the API interacts. So for instance, we might be making some kind of mathematics API, and we might want to assume that everyone is always going to interact with the sine, cos, etc. functions with radians, when actually the API we're interacting below that is taking degrees, or is taking degrees and radians. So there we've assumed something, and we've changed the API because of that. Now, we haven't really simplified much there, but you can see how by baking in assumptions about the way things are used, and by assuming a context in which they're used, we can simplify, reduce the number of methods needed to do the same thing. We don't need to convert between radians and degrees if we're always using radians. Now, some assumptions, like possibly the one that we would always want to use radians, are either annoying or downright unreasonable. And that's fair enough. There are a lot of bad assumptions out there, and these can negatively affect APIs dramatically. And, well, any kind of abstraction which uses bad assumptions can negatively affect the abstraction and make it useless in some contexts. So we can actually consider the idea of APIs and more generally abstractions taking information and the way they expose lower layers, we can consider that in relation to information theory. I don't want to get too deep on information theory here, because obviously that's not the point of this talk, but in information theory we have an idea of the entropy of something, and that's the information content of that thing in an abstract way. So if we have a particular amount of information content of something, say an API, that is all the different things that API can express. And if we provide access to the whole of that API, we probably can't really change it in much way. But if we have some kind of assumption about the use of that API, i.e. if we know that some of these methods aren't going to be used at all, others are only going to be used in certain ways, this is comparable to the way that we can consider information exchange in information theory. I.e. if we know only a particular type of message is going to be sent, we can compress things by only supplying representations for those messages that we need to send. Obviously that's an oversimplification, but you can see how you can really start to consider APIs and abstraction in general as a form of compression. Now, interestingly enough, in computing, typically this is a lossless compression in that we can reconstruct exactly the original information. As I was saying earlier, we're just hiding information, we're using assumptions, etc. to simplify. We're not entirely removing information. Whereas with our the mathematical abstractions which remove content, they remove information that's not necessary, that could be considered really a form of lossy compression, i.e. a kind of simplification which removes some of the information, so we can never properly reconstruct the original. But just like an MP3, which is a lossy media encoding format, really that kind of abstraction doesn't remove anything when used correctly, because we can still hear all that we need to hear in an MP3 mostly, and we can still get what we need out of that abstraction. Asymptotic complexity is still useful. Just because we've removed information, it doesn't make it less useful. In fact, sometimes it can make it more useful. So this allows us this compression, so to speak, with the use of assumptions or analysis of the way that things are used with context. This allows us to be more concise while also representing the same amount of same interface, as long as our assumptions hold. When our assumptions don't hold, i.e. when the way we assumed the interface, the abstraction, etc. would be used are incorrect, then it in fact makes it harder, if not impossible, to represent what we want to represent using that abstraction. Now, there are other forms of abstraction, and one of the most common forms of abstraction, apart from APIs, libraries, etc., is object orientation. And object orientation is really an implementational variant of the concept of ontologies, i.e. the concept of how things are related to each other, how objects, or in ontologies, things are related to each other. So we may have some object which is a particular kind of car, as an example in a second, and then that might be related to a car, and that might be related to it in the set of things that have wheels, and so on and so forth. So we have these abstract properties and the way they interrelate. I'm simplifying things, but you can go look into ontologies in computing, and they're quite an interesting topic, and really they are analogous to the way object orientation works in many ways. They have slightly more complexity than that, but they are a way of abstracting in the same way object orientation is. They're pretty analogous. I'll just talk about object orientation from here, but that is an interesting area to look into, particularly the relationship between the two. So with object orientation, we're abstracting away specifics of something and instead allowing ourselves to consider the ways in which different properties of objects are shared. So we may have some number of these abstract objects which have properties but they're not a full object until they're combined together into some kind of concrete object. So instead we're grouping behaviours and allowing their combination. And doing that allows us to consider the behaviours in isolation and then allows us to combine them without necessarily knowing what's happening. So we're hiding the behaviours inside these objects. So here's the obligatory car-based example. I think this is pretty much the one that's always used, or related to the one that's always used. So here I'm going to talk about properties, but really what we're talking about here is objects in general, or abstract properties of objects which can be shared. So here we have two different properties, two different behaviours. The behaviours for things that have wheels and the behaviours for things that have an engine. And we can combine these together with some extra information in a car. So here's the behaviours for how a car works. And then we can have a specific instance of that. So what we're doing here is we're encapsulating the behaviours that are related and then allowing their combination at a later date. But importantly, we don't have to know how these behaviours work necessarily. And this can be implemented not necessarily with object orientation. There are a number of analogous systems for grouping behaviour like this. Object orientation is the most well known. And really what they're seeking to represent here is the same idea behind ontologies, the fact that we can relate things and we can abstract behaviours, and we can create these diagrams of inheritance of behaviours or of relation between things. And most object orientation systems do at their core have an object which is just an object or a thing or this abstract base which everything can be related back to, in the same way ontologies have a concept of a thing which everything can be related back to. So, as may have become evident, or maybe not, talking about that and talking about APIs, a core part of being able to do this generalization, about being able to do this abstraction, is compatibility, the ability to use the same thing across multiple platforms, or the ability to interchange things which share an API, which share an interface language between each other. Now, compatibility is an amazing thing to gain through this, because it means we can change things underneath stuff and it'll still be compatible. We can change platform, we can change the hardware beneath something, and it's all compatible still, mostly at least. However, a lot of that is lost if we are simply creating these abstractions without some kind of restriction. i.e., once we've created some kind of abstraction, we need to be sure that that abstraction, at least if we're not the only one using that abstraction, we need to be sure that abstraction stays the same. We need to be sure that that API, that object-oriented hierarchy stays the same, or at least doesn't change in a breaking way for it to be useful. Now, not everyone necessarily agrees with this. Some people are of the opinion that we should allow these things to change, and then people should change their use of the APIs to account for this. But either way, it is important that this be consistent. I think it's important that it be consistent. So, as an example of this kind of restriction, I'll have a look at something called semantic versioning, which is just one example of the different ways people have attempted to approach the idea of consistency and compatibility, and allowing this under certain restrictions. So semantic versioning at a high level is just the idea of having some way of telling whether or not you'll be compatible with something. So for instance, if I look at the version number of an API, of a library providing an API, will I be able to Will I be able to upgrade my, to use that without needing to change my code, something like that. And it's concepts like these which really underpin most of the restrictions on changes to these APIs, on changes to abstractions. And without them, it can be difficult, if not impossible, to maintain our compatibility between these things, to keep up to date with things. But for semantic versioning, the idea is that you have major versions which represent breaking changes, i.e. changes to the core of the API, which mean that old things will stop working, say removing a method, any method. So if Windows removed the getText method, or getWindowText method, that would be a breaking change because probably someone relies on that. So that kind of change is a major change. And what's interesting with semantic versioning is that it suggests that any of kind of change like that is, even if you're sure no one's using it, you should still call that a breaking change, which makes sense because you can never really be sure. But at the same time, it's considered by some to be a very a harsh line on it. And there are minor changes, which are those which are still backwards compatible, i.e. adding a new function. That's typically perfectly backwards compatible. It may be a problem if anyone wants to go back after to an older version, because it may not exist anymore, but that's their choice. And then there is the patch part of the version, which is if we have some kind of change that fixes some issue in the way that it was implemented. So here we're talking about correcting an issue. It's even a smaller change, hopefully, than a minor change. So this way of restricting changes to APIs, to abstractions like hierarchies of objects, etc., is a requirement, or at least a necessity if we want to provide compatibility that's reliable. The alternative to this is to do a more complex method in which we actually try and change things but catch the cases where people are still using the old way, which is much more complicated, but has been done in the past. Now, this is something we actually see with the move from the Win16 API to the Windows 32 API, which happened with the move from older Windows versions to Windows 95. Now, in this move, we see the move from the low-level interaction, which was possible in previous versions of Windows, with the Win16 API, which actually lots of things just ignored, or they did things with the Windows internals that they weren't supposed to. And for the first time with the Win32 API in Windows 95, we had things like memory protection and multitasking come in, which meant that it was really impossible for them to do this in the same way. And this meant that many things ended up breaking, which weren't necessarily meant to, and many things didn't work in the way that we assumed they would. One side effect of this was that Windows had to do a lot of work because they wanted to maintain backwards compatibility with all of the operating system's previous applications, or as many as possible, and so a lot of work was done to maintain this compatibility, which ended up being almost entirely successful. There were still a lot of issues, particularly with games, but in the end they managed to catch a lot of these special cases and handle them, which caused a lot of people a lot of headaches, I'm sure, to do. But you can see how by not being able to restrict the interactions with the system, without being able to restrict the interactions with the APIs here, then a lot of the advantages of abstraction were lost. Suddenly, even though we maintained the same methods mainly, everything should have just worked, except it didn't, because lots of things weren't using the abstractions. They were bypassing the abstractions. They were going inside to areas that were not so-called API areas that had a consistent interface. And this meant that suddenly things just stopped working. Which, big changes like this If we look at the semantic versioning outlook on this, this was to be expected. It was a major breaking change, and therefore we should have just dropped support. Windows obviously didn't want to do this because it would mean that people didn't really want to move to their new operating system. So instead, they spent the effort to make it compatible, but at the same time, this cost them a lot of time and money. Now, I've talked a lot about abstractions and some of the ways we see abstractions in computing. And I think it's important to step back for a second and see really how we can benefit from them beyond just the basic use of them every day in the way programming languages, etc. work. So, I think this is some of my outlook on abstractions, really. So, I think when creating things for computers, it's particularly important to always search out abstractions, to find the places in which we can approach things in an abstract way, and use those really as stepping off points to consider the whole of our problem in an abstract way. If we're not considering things abstractly and considering where we can make these abstractions, then we can end up creating a system that, while it works, will not be able to do anything else ever, will not be able to be expanded, will not be able to be worked on by anyone else, because really it's too ingrained in the way that things are actually implemented and isn't considering things in an abstract enough light. Now, we can also see that APIs are a powerful tool throughout this. They allow a consistent interface, they allow us this compatibility if we use them correctly. And I think it's important to not just use them correctly when we are actually creating explicitly an external interface, but I think really we must consider most things that we do to be implicit APIs. When we create something, even if no one else will ever depend on it, if we consider it as an API, as something other people may depend on, then this lets us think more carefully about the way we structure things. If anything we publish is good enough to be an API, then that means it's good enough for you to come back to and edit later. Because really, with all abstractions, if we are working in an abstract way, if we are structured, if we consider how the next person using it will approach it, how they will be able to use it, this benefits everyone and even ourselves, because the next person using it is usually you, but far enough down the line that you've completely forgotten how it works. So really, abstractions and architecture go hand in hand with this. The architecture of something is fundamentally usually an abstract architecture, and by always thinking about the way we can abstract, we're always thinking about the architecture and the abstract architecture that we're attempting to implement. And this can be really important, particularly when working with others. If we're doing our own programs, then sure, we can do random stuff that doesn't make much sense, and that's kind of fine as long as we never want to come back to it and no one else ever wants to use it, which sometimes is fine. But for the majority of work, particularly work with others, we need to consider our architecture and we need to consider our abstractions that we use in that architecture to achieve an interface that is consistent, that is useful, that is extensible, that we can add to later. And without considering abstractions and without considering architecture, that's difficult, if not impossible, to do. I think really I can't hammer home hard enough how useful it is to consider things in the abstract and to consider the way we use them. You know, everything we make can be treated as something someone else will use, as some library, as some abstraction on a lower layer, and therefore it's useful to be able to think in an abstract way, to be able to create these abstractions in a useful way that allows others to build upon them. So I think I've talked a lot here about abstractions and different things and my opinions on them, as well as some of the more concrete aspects of them. But I think it's important to remember that no matter what you may you may go away and not really try and think about things in terms of internal APIs, in terms of libraries, etc. But it is important to remember that abstractions are the core of computer science, really. So you can't get away from them. All of computer science that is implementation related, at least, relies on abstractions, as does most of science in different ways. And software engineering also relies on these abstractions, less so on the mathematical kind. We may consider the asymptotic complexity of something and so on, or we may consider an abstract algorithm, but really, most of the time it benefits from the more concrete abstractions that we've mainly been focusing on here. But these are still core to things we implement, to things we do. And really, I think it's important to just remember that you can go away, and if you look, you can find abstraction everywhere in computer science, and you can find many different ways of looking at it. Not just in the context of object orientation, in the context of APIs, not just considering things like information theory. There are many ways we can look at abstraction, and I think it's important to continue to bring new outlooks to it. I could go on and on all day about my opinions on this, but I think I'll draw it to a close there. So thank you for listening to me waffle on for what should hopefully be half an hour once it's been through the editing mill. Yeah, I have quite a lot of references for this, so I'll leave them up on screen. And I guess if you're watching this live, I hope to see you afterwards in Discord to discuss this or answer any questions you may have. Thanks.